Hi. So this is the first lecture recorded from my home studio, so bear with me here. I'm going to start the slideshow. So today we're going to talk about electromagnetic induction, and to do that you can't miss talking about Michael Faraday. He was a British physicist and chemist and a great experimental scientist. He did most of his important work in physics in the early to mid 1800s. And he helped invent the motor, the generator, the transformer, and electromagnetic induction, which is the topic of today's lecture. So Faraday really wanted to understand, if a current creates a magnetic field, can a magnetic field also create a current? Skipping ahead, spoiler alert, an induced current is produced by a changing magnetic field. A static magnetic field won't do it, but if you have a changing magnetic field, you can get an induced current in a circuit. So to do that, you have an induced electromotive force, or EMF, or voltage, which is associated with that induced current. And Faraday's law predicts in an equation what that induced EMF will be. So what you can see is that a current can be produced without a battery present in the circuit if you have a changing magnetic field. And Faraday's law of induction describes that induced EMF. So here was sort of a schematic of Faraday's experiment. What he did here was he had a primary coil, and that primary coil was connected to a switch and a battery. And in the primary coil, you could generate current through the circuit by hooking it to the battery. Then what he did was he had a secondary coil, and it was also wrapped around a ring, and there was no battery present in that second coil. Now what Faraday observed was that there was no current in the secondary coil when there was a constant or static current in the primary coil. However, he noticed that when he opened and closed the switch, there was a brief induced current in that secondary coil. So the ammeter would change from 0 to one direction and then return to 0 when the switch was first closed. And then when the switch was opened to shut the current off, the ammeter would change in the opposite direction and then return to 0. On this slide, you can see Faradays Sketch, which was published in his paper in the early 1800s. He also noticed that the ammeter, of course, read 0 if there was a steady current or no current in the primary circuit. So he concluded from this that an electric current can be induced in a loop by a changing magnetic field. So a static magnetic field won't do it. You have to have a changing magnetic field. And then the induced current exists only while the magnetic field through that loop is changing. So to sum up, an induced EMF is produced in the loop by a changing magnetic field. So the existence of magnetic flux isn't sufficient. The magnetic flux also must be changing. And that's expressed here in this equation. Here, the curly E here is the induced EMF, and that's equal to the negative derivative with respect to time of the magnetic flux, phi b. Okay? In English, that says the EMF induced in a circuit is directly proportional to the time rate of change of the magnetic flux in the circuit. So to remind you of what magnetic flux was, we did cover this in a previous lecture. But to sum up, the magnetic flux is the magnetic field that pierces through an area. If you call the area A, then you could say that magnetic flux is equal to B dot A, the magnetic field dotted with the area vector. Remember that the area vector for an open surface, like a loop, for example, would have a magnitude of the area of the loop, and then the area vector points perpendicular to the plane of the loop. So, for example, if here my hand is the area vector, then my finger pointing out here would be the area vector pointing out from the loop. Okay? Now, the magnetic flux is the dot product of the magnetic field with that area vector. So when you take the magnitude of your dot product, you get the magnitude of your field B times the magnitude of your area A times the cosine of the angle in between the magnetic field and the area vector. Okay? All right, now if your magnetic field isn't constant over your loop, or if you have a funny shaped area and you can't just write out straight the area, then you can calculate the magnetic flux by doing the integral of B dot dA, okay? Incidentally, the SI unit of the magnetic flux is the Weber, named after this guy, Vilhelm Weber, who was a German physicist. He did important work in electromagnetism, and he was the co-inventor of the telegraph. And in SI units, 1 Weber is 1 Tesla times meters squared. Okay, now, as we said, the magnetic flux is equal to the integral of B dot dA over your area, okay? And if you want to be perfectly correct here, the EMF is not just minus d phi b dt. If you have more than one loop, for example, if you have a coil of wire with multiple turns of your wire around a loop, okay, then to get the total EMF induced in that coil, you would have to take negative n, where n is the number of turns, times d phi b dt, okay? And the d phi b dt here would be for one loop, and then you multiply times n, the number of loops, all right? Now, you can induce an EMF in many different ways. First of all, you can change the magnitude of your magnetic field with time. Second, you can change the area of your loop with time. And third, you can change the angle, theta, between B and the area vector with time. And if you do any of those things, then you'll induce an EMF. And you can also do some combination of those things, and you can induce an EMF. So let's talk about motional EMF to finish up today's lecture. So motional EMF is a voltage induced in a conductor moving through a constant magnetic field. So here you can see a bar, a metal bar, moving to the right through a magnetic field which is into the screen. The into the screen is indicated by the X's, the green X's on the page that gives the direction of that magnetic field. Let's say that it's a conductor, so it has free electrons, like a metal, okay? And it's a length L, and it's moving to the right with some speed V. Now those free electrons, when they move through the magnetic field, you remember that there's that Lorentz force. F is equal to QV cross B. So if you have charges in your bar there, which you would if you had free electrons, and they're moving to the right, then you can see that you would have a force on those charges. Now it's indicated in your slide, if you have positive charges in your bar, then it would be QV cross B. The V is to the right, B is into the screen, and so the force on positive charges would be up. So the positive charges would move towards the top of the bar. Now, because we're flipping the sign for a negative sign, that means that the force on a negative charge would be downwards, okay? And so if you have free charges, those charges, because of the motion of the bar through that magnetic field, will migrate until they can't move anymore, okay, till they reach the limits of the bar. Now what that does is, of course, just like in the Hall effect, separate those charges. So you have the positive charges on one side and the negative charges on the other. And remember, of course, that if you only have free negative charges, that the absence of the negative charges would cause a equal and opposite positive charge on the other side, okay? That establishes an electric field within the bar. Now what will happen is that, very similarly to the Hall effect, the charges will migrate until the electric field is established that will balance out the effect of the magnetic field, okay? So once they balance out, then you have the electrostatic force on a charge upward and the magnetostatic force on that charge downward, and they balance one another until the free body diagram, the forces sum to zero. That's at equilibrium, and then you have the magnitude of those forces equaling one another. So you would have the force due to the electrostatic QE equaling QVB. Now, there's no sines and cosines here expressed in this equation because everything is 1. Everything's 90 degrees from one another or parallel. So you have QE is equal to QVB. Now, because the charge appears on both the left and the right-hand side of that equation, you can say that E is equal to VB. All right? So, in other words, the charges will move in response to moving through that magnetic field from the Lorentz force law, F is equal to QV cross B, and they move until there's an electric field that's big enough to keep them from moving anymore, okay? So when an electric field is established, of course, that sets up a voltage. Remember that your voltage is equal to the negative integral of E dot ds. So if you have a nice straight conductor like that and everything's constant and everything's holding still and straight, then your voltage would be equal to your electric field magnitude times the length of that bar, L. So your EMF, your established EMF would be your electric field times L, which would be equal to BLV. Okay? The BLV comes from our equilibrium setup there. QE is equal to QVB, E is equal to VB. So if you plug in for E, VB, then you have BLV. All right? So this potential difference between the ends of the conductor is maintained as long as the conductor continues to move through that uniform magnetic field. Now, if you move it the other way, if you cause it to change direction, what will happen is that, of course, the direction of the velocity vector will flip, and so the sides that the charges line up will flip. So if you had positive charges on top moving to the right, then if you move to the left, you'd have negative charges on top. Let's do an example problem because they're worth a million words, maybe even a billion. An ocean current flows at a speed of 1 meters per second in a region where the vertical component of the Earth's magnetic field is 0.35 Gauss. The conductivity of seawater in that region is 4 inverse ohm meters. So assuming that you have only motional EMF, find the current density J of the horizontal electric current. And then as a follow-up, if you were to carry a bottle of seawater through the Earth's field at this speed, would such a current be flowing in it? Okay, so here we have the equation for E is equal to BV for motional EMF. Remember, this was when the forces balanced out, okay? So here, E would be equal to V times B, which is the speed of the charges moving through times the magnetic field. Now, the magnetic field was given to us in Gauss. Remember that there's 10 to the 4th Gauss and 1 Tesla. So writing this all in SI units, the electric field would be equal to 1 meters per second times 0.35 times 10 to the minus 4 Tesla. When you multiply those things through, of course, you get 0.35 times 10 to the minus 4 volts per meter for your electric field. Now, remember Ohm's law. Your current density, J, is equal to the conductivity, sigma, times E, your electric field. So if we multiply the conductivity of the seawater, sigma, times our electric field, we should be able to find the current density, J. So here we have 4 inverse ohm meters times 0.35 times 10 to the minus 4 volts per meter, and that gives us our current density, which is 0.14 milliamps per meter squared. So we found it. But now the follow-up question, let's think about that for just a second. The follow-up question said, if you had a bottle of seawater instead, and you carried it through the Earth's magnetic field at that speed, would you still have that current? Okay? Well, the answer is no. Okay? The deal is that if you had a bottle of seawater, what would happen is you'd be carrying it through the Earth's magnetic field, sure, and then you would establish an EMF, sure, but eventually you'd run out of charges. The positive charges would move to, say, the top of the bottle, and the negative charges would move to the bottom of the bottle until you exhausted all the charges that you had, and then the current would stop flowing. So you'd have a voltage with charge separation, but once it reached its static condition, you'd have no more current. It would stop flowing. And it would do that in a remarkably short period of time. The reason it works for ocean currents is because you have so much water that you have a nearly inexhaustible supply of ions. And so the current density will keep on going. It'll keep on trucking because it can just pull from the ocean for more and more and more charges. Okay? Let's do another example problem and use that to follow up with another idea behind motional EMF, or one of those ubiquitous problems in physics whenever people talk about motional EMF. And it's this. Assume there's a conducting rod being pulled to the right at a speed v while maintaining contact with 2 rails. A magnetic field points into the page, or into the screen here, I guess. We know that an induced EMF will cause a current to flow in a counterclockwise direction around the loop. The charges move and the wires heat up. So something is doing work. Is it the magnetic force? And if not, what? Okay. So first let's do the setup for this problem. Let's look at the picture, okay? Here we have a bar, which is indicated in blue here, moving to the right with the speed v, and that vector for the velocity is indicated in red here, okay? Now, in our little equivalent circuit diagram, what we're going to do is we're going to assume that all the resistance of the whole circuit, probably from the rho L over A, okay, we're not going to put a little external resistor in there, but what we're going to do is assume that all the resistance of the circuit from the rho L over A contribution gets pulled into an external resistor, which I've drawn here as the red zigzag line, okay, in the equivalent circuit. All right? We're going to assume that everything else is just a perfect conductor and doesn't have any other resistance just due to its length, okay? Now, the bar being pulled to the right, and then there's a magnetic field indicated by green X's into the page, okay? So that's our magnetic field there. So what's going to happen is that, of course, there's going to be a motional EMF induced in that moving bar, okay? The magnitude of the motional EMF, as we've discussed in other examples, is BLV, where V is the speed, B is the magnetic field, and L is the length of the bar, all right? Now, let's think about it just a second. In order to keep that velocity going to the right, if you have charges moving to the right, BLV, in the magnetic field, then what's going to happen is that there's going to be an IL cross B, a current IL cross B force there, okay? So here you have IL cross B. In that blue segment, the current is flowing upward through the bar, and so IL cross B will be to the left. So because the fact that you have a current moving through that bar, you're going to have a force due to that magnetic field, IL cross B, to the left. But the velocity is to the right. So in the absence of an external pull to the right, the bar would eventually just slow down and stop moving, okay, because of that externally applied force. So in order to keep the EMF going, in order to keep the voltage and the current flowing, you're going to have to pull to the right with some applied force. The amount of applied force that you would have to apply would have to be equal in magnitude to the magnetic force from the IL cross B contribution if you want to have a steady V, if you want to have a steady speed, all right? So where does the work come from? Well, it's got to come from that applied force. In other words, it's got to come from whatever agent is forcing that bar to keep moving at a constant speed V to the right, okay? So that's where it's coming from. But now let's consider some equations that we might use when we're doing this, ever-present ubiquitous problem and example in physics of this bar on sliding rails. Okay, so we have an induced EMF. According to Faraday's equation, the EMF is equal to negative d phi dt, where phi is the magnetic flux, okay? Now, if you plug in for that magnetic flux, the angle in between the area vector and the magnetic field, that cosine, gives you 1, a factor of 1. So the magnitude of your dot product would just be B times A. B is a constant. It comes from the outside somewhere, an externally supplied magnetic field that doesn't change. And so what is changing, though, is the area of your loop, okay? Now, in this case, the area of our loop is a rectangle. The rectangle has sides x, which is the distance between the left-hand side of our loop and wherever our bar is at a given instant of time, okay? So it would be that x times the length of our bar, right? So the area of our loop A would be Lx. But the area is changing with time. Now, L doesn't change. It's a constant. The length of our bar stays the same. But because our bar is moving to the right, our position x does change. So when we take this derivative, negative d phi dt, we end up with negative BL dx dt. Now, dx dt is just our velocity, v. So we can say that our induced EMF is minus BLV. Okay? Now, that induced EMF would be equal to the current I times the resistance of our circuit. Now, we visualized this resistance as just being in one little external resistor, and we called it R, okay? So we have now an expression for our current. Our current would be our induced EMF divided by that resistance, and our induced EMF is BLV. So the current in the circuit would be BLV over R. Like I said, the applied force has to be doing the work in the bar, okay? And you can figure out how much power you'd have to supply there. So remember from our first semester physics class, we said that power, which is energy per unit time, would be F dot V, okay? So in this case, the power for our circuit would be F applied times our speed V. And then that would be equal to, P is equal to IV in the circuit, okay? All right, so since you have here the force applied, the force applied would have to equal in magnitude the IL cross B force. And so that gives us ILB times V there for F applied times V. And then the power in a circuit would be the induced EMF squared divided by the resistance of the circuit. So these equations are handy dandy little equations if you want to try this out in some homework questions. Okay, I hope that helps you out, and I'll see you around, okay? Let me know if you have questions.